And these are actually seen because this is a process that you can do at any time scale, right? You can do it with high-line Rydberg states and microwave pulses, so that this can end up on an oscilloscope, and they just see this. Now, we're going to work in the optical, and so we're not going to be able to see it on an oscilloscope per se, but this is, this is what's happening. So again, this is the idea that the input field went in and something got generated that's kind of out of phase with it. And so we had in frequency the input pulse, and in time it looked like this. And it goes to looking like something that has a sharp absorption feature in it and these temporal beats going through it. And this is an absolutely very, very generic picture of what happens when you put a broad pulse near a narrow resonance. And it was first understood at least as far back as Mossbauer spectroscopy around 1960, because it's very, very necessary. You know that in Mossbauer spectroscopy you have these really, really narrow absorption and emission features. And so any pulse in the world is broader than the Mossbauer spectral features. And so they had to understand this to understand what the lifetimes they were seeing were. And this is just a cube calculation. I don't really want to say much about it, but even in this sort of three-level system, if you add an IR pulse, you can get very, very interesting things. And this is based on the references on the next slide. Sorry about that. But this is based on the idea that you would have absorption going on, and when you turn on this IR laser, if it's resonant with this 2S state down here, then you can basically control the phase of the population that you're exciting, such that you can turn the system from absorbing to not absorbing. Now, it's not quite that simple, but that's basically the idea. And so, for instance, here we had a calculation where we put in a 60 femtosecond IR pulse that is resonant with this 1S2P thing. And so, if we did the calculation without the IR pulse, what would come out would be just a greatly reduced envelope with this tail behind it. But what we do here is for the 11 femtoseconds right in the middle of the XUV pulse, we turn on an IR pulse that couples the 2P state to the 2S state. And that turns off the absorption in the system, or more directly, it modulates it. And it modulates it in such a way that it reshapes the generated field. And so what comes out is actually a shorter XUV pulse. It is just about 11 femtoseconds. So it's as if you have opened a transparency window for 11 femtoseconds right in the middle of the pulse. It's not actually quite that simple. It's actually, you really are controlling the phase, and you're cycling population around here. And one way you know that is that this 11 femtosecond thing that comes out of the gas is shifted by 4 femtoseconds. And that is actually the round trip time that it takes the amplitude. It's the Rabi flopping time. It takes the amplitude to go down here and come back up, because when it goes around once, it has the wrong phase, and it turns the...
So this is a version of EIT, right?
Thank you so much for saying this. No, Marlon Scully will now kill us both instead of just me.
You on camera?
Why would you kill it by both?
Like he cares. It's not an interference effect in the sense that the EIT people talk. It's much better to think of it as an Altler-Towns effect, as an Altler-Towns splitting.
Okay.
So,
it sounded like EIT.
It is. It does, and it's been talked about that way. And then various quantum optics people, as Linda will tell you, get very, very upset. So, I mean, the reason that Linda knows all this is right. Yeah, I mean, this is one of these things where people start yelling and it's not worth it. Right. And so, I mean, it's based. The idea was based on it. It's just a much cleaner version of an experiment that Linda Young did based on ideas that Robin Santra and Kristen Booth had. And they did this, they managed to very heroically make this work with an X-ray pulse. And so they had the X-ray pulse and they had a coupling laser, and they really were able to control the absorption. And I don't want to talk anything more about it, except to say that for me at least, this was a real inspiration, this experiment, to think about controlling polarization and for meta as well. So now I want to get to talking about transient absorption. We're going to have the IR pulse there the whole time. So transient absorption, as we say, is a well-known technique for studying quantum dynamics because you can follow fast changes in the polarization by changing the delay. What you basically look at is the change in the spectrum, so you look at that differently. The usual case, the IR pumps the system and it starts the clock, but in this case, it's the XUV that's going to do it. There's no constraint on frequency, resolution versus delay, frequency versus delay, because delay is not time. In other words, we're looking at complete pulses going through with the spectrometer not distinguishing time, right? All you know is the frequency spectrum that came through. And you don't know at what time the processes happened, at least not a priori. So that's why the uncertainty principle doesn't take, right? All schemes take advantage of the synchronicity between the XUV pulse and the mated. The first extension to the attosecond domain was this experiment done in Ferenc Krause's lab in collaboration with Steve Leone and Dan Newmark, and that was very different than what I'm talking about. So this is a paper in Nature in 2010. Here the IR pulse really was the pump. It ionized the system and then they probed the system with the XUV. That's not what we were talking about. So we want to do the transient absorption in neutrals. So the XUV pulse is going to pump the system and start the clock. The XUV pulse too weak to excite the system. We'll look at the change in optical density. That's the fancy word for it. We'll look at the energy that gets taken out at each frequency as a function of the delay. Once excited, the electrons experience the IR field as strong. So there's fast ionization, strong couplings. And there's lots of experiments that have been done in these type systems now. This is an incomplete list of people that have been studying this experimentally. So this I talked about the other night. So the question is, in the picture we're using, absorption is a macroscopic phenomenon. I just said it's an interference phenomenon from the generated fields. Can I think of absorption at the single atom level? And the answer is yes. So I just want to go through this because it's kind of interesting to think about, can you do this? So at the single atom level, what can you think of, since I don't have photons and things? Well, at the single atom level, I can think about the energy that gets absorbed from the beam by the atom. In other words, I can keep track of how much energy has the atom absorbed, and I can relate that to the energy that must have been lost by the XUV pulse. And so I start with my standard Schrodinger equation, one electron, in a pseudopotential Schrodinger equation for linear polarization. It looks like this. Here's the field, here's Z. The plus sign is correct because this is not the dipole, it's the Z operator, and the charge is negative. So here's the thing. Here's what I'm going to use to do this. I'm going to say the energy that gets gained by the atom is going to be the integral over the whole pulse, so over all time, of the rate at which it gained energy. Who could argue with that, right? So now I can use the Feynman-Hellman theorem and the TDSE here to prove that the rate at which the energy changes, time derivative of the expectation value of the Hamiltonian, all the terms that involve d psi dt cancel out when you use the Schrodinger equation. All that's left is the partial derivative. In other words, does the Hamiltonian have an explicit dependent on time? Why, yes it does. That's in the electric field that's driving the whole system. Right? And so you end up with the rate at which you're gaining or losing energy is equal to the expectation value of the Z operator, so this is proportional to the dipole moment, times the rate at which the electric field is changing. Now, the expectation value of the Z operator is, I'll call that Z of t. The dipole moment in the system is minus that because of the negative charge of the electron. So here is my expression for the energy gained by the atom over the whole pulse. And it's written here in terms of the Z coordinate and the time derivative of the electric field. You can transform this by using the integration by parts into something that involves velocities and the electric field, or the acceleration and the interval of the electric field, whatever you like. It's all, so this is it doesn't look like it, but it is a gauge-independent number that will agree no matter how you calculate the wave function. And so now I want to define something. I want to define this capital lambda. It is the Fourier transform of the dipole moment that we get out of the whole calculation times the complex conjugate of the field that's driving it. So the tilde is here, that's always Fourier transforms. And so now, just by plugging the Fourier transforms of these things into my equation for the energy gain, I can now express the energy gain in the frequency domain. It's minus I times omega times this lambda of omega thing. And now I have a little bit of stuff that's just definitions. The dipole moment, d of t, and the electric field, E of t, those are real functions. So that constrains their Fourier transforms to have this symmetry. All right? They have to be odd functions. And so this lambda has that same thing. And so now we can use these properties to re-express the energy gained over the whole pulse as 2 times omega times the imaginary part of this lambda function. So this is the energy gained by the atom over the whole pulse expressed in the frequency domain. And it comes from, mechanistically, I want you to understand, it comes from doing a calculation, single atom calculation, keeping track of the dipole moment for the whole pulse, Fourier transforming at the end, multiplying it by the Fourier transform of the driving field, complex conjugate, take the imaginary part, here's the energy that gets gained over the whole pulse. But now I've done something that I wanted to do. My original expression was just an integral over all time, so it's very opaque. But now I have the energy gain broken down into frequency components, right? So this begins to look like something like a cross-section, right? Because the energy gain looks like omega. You could think of that as h bar omega, right? Here's the energy gain times a probability for being excited per unit frequency. So this starts to look kind of like a cross-section. And now there's just a few more steps. So this again is my expression for the energy gain. So this lambda, if I were to divide it by the flux of incoming radiation, this now looks like a generalized single atom susceptibility. It looks like something where the imaginary part corresponds to absorption or emission. And although I'm not going to use it in this talk, the real part of it corresponds to dispersion. It would tell you whether the light was traveling. It would tell you the extra little bit of phase that got added per unit frequency to the field by this interaction with this single electron, with this single atom system. So I'm not going to use that, but I just want to say that's kind of what it looks like. And the reason I say generalized is because the sign of this is not fixed. I could have absorption or emission, right? And I could have any kind of dispersion I want in principle. So what we do is we talk about the imaginary part of lambda. We talk about that as a single atom response function, this S of omega, and it depends on delay. That's what tau is. And looking at this, you can just read it off. It's 2 times the imaginary part of the dipole times the complex conjugate of the driving field. It is an absorption probability per unit frequency. And it's tied to the pulse that you're using, right? In other words, different pulses will make different d of omegas here. And so now this is kind of nice because we can write the total energy that gets absorbed by the atom as just the weighted integral over this response function. So I take S of omega, I multiply it by omega, I integrate over all positive frequencies, and I get this energy gain. This is these two things multiplied together are an even function of omega. So I mean, you could integrate over the whole spectrum and then just take out the factor of 2 there. But there's no need to. There's no new information at the negative part of the spectrum. A nice thing about this is you could say, at the single atom level, if I'm absorbing energy, that's because I got excited, right? So you could ask the question, at the end of the pulse, what is the probability to not be in the ground state anymore? And you can show that if you take this response function and integrate it over all frequency, it will give you the change in population. And this is an important check. You can do it from you can check your calculations this way, and it really does work. So we've done something that we really wanted to do was we wanted to think about when the system gets excited and the IR pulse, moves population around. what is happening as a function of frequency, right? And this response function really tells you that, but we calculate it from a time-dependent thing. Now here's a nice thing. You can go back, you say, well, how does this single atom picture match up with this interference picture in the gas that you gave me before? And the nice thing is that this interference term that we talked about before in the thin gas limit, this is exactly related to n, where that's the number of atoms, times omega over c times the single atom response function. So the single atom response function really is telling you the amount of energy absorbed or emitted per unit frequency per atom as you in the thin limit. So you can look at this either from a Maxwell point of view or from a single atom point of view scaled up. And this, of course, now allows people to yell at each other about things that don't matter. And you can get very interesting referee reports and stuff like that. Because some people feel like this is really fundamental and this is kind of accidental, and other people feel like this is really fundamental, and yeah, it goes to that. And this proves that my equations really are coupled in the way that I said they are, right? This is good proof that the energy is going to disappear from one and show up in the other. And then, of course, if you want to have more layers of the gas, well, you really have to, worry about solving a couple of equations. So we have this frequency-dependent response, and it's an absorption probability per unit frequency. Dividing this by the flux of the incoming radiation, that gives you a generalized cross-section. Now, the incoming flux is proportional to the intensity, so the generalized cross-section is going to be omega times the imaginary part of this lambda function divided by the spectral intensity that you had sent in. In other words, this is how much energy do you have per unit frequency at a frequency omega. And this will, again, this is proportional to the E of omega squared. So when you take it's a real number, so you can take it inside the imaginary here, and it will cancel the E star, and so you just get this, which is a really standard, in chemistry, a really standard expression for the cross-section. The alpha here is the fine structure constant because I've done this in atomic units. If you want to do it in SI units, it comes out looking like this. But the point here is that because we have these two fields and we can redistribute the population all over the place, this sigma can be positive or negative. At any given frequency, energy could be added or subtracted because we can move it around, right? We're going to conserve overall energy, right? But we can do these sorts of processes. So this can be positive or negative, and it can include processes of many different orders, what Brett was calling photons, right? In this picture, a 2-photon process is a second-order polarization process, right? 3 photons would be a third-order process. 1 photon would be a first-order process, right? So if you did everything in the frequency domain, you would have to write out expressions for each of those things. What's my first-order response? What's my second-order response? What's my third-order response? And, oh, the different frequencies are coupled, so your head would explode. But in the time domain, you just do the calculation, and then you Fourier transform at the end, and you get all the information. So this is always a nice thing about doing time-dependent calculations. So now let me look at some transient absorption things. So I just want to look at the single atom response, and want to calculate that. One nice thing about the single atom response is, because of the form of the function, where it's the dipole response times the driving field, if there's no driving field at a given frequency, then there's no response, right? And so I just get 0, and that's very good, right? The cross-section should also be 0, but that's trickier because the dipole response should be 0, and the field at the frequency should be 0, and those should give you 0. You never want to calculate 0, right, in a numerical calculation. You never want to try and calculate 0. It's right, because you have to get everything exactly right. So you want to have something that's 0, by itself if it's supposed to be 0. Okay. So that's why we think about the single atom response rather than the cross-section. You can go back and make it a cross-section afterwards. So here is a single atom spectrogram for one of these calculations. 800 nanometers, helium, EUV pulses, 330 attoseconds. It's centered up here near the ionization limit. It's very broad. The IR cycle is about 11, the IR pulse is about 11 femtoseconds long. And this is the spectrogram. So here's delay. Here I show you the IR pulse intensity envelope. So at a delay near 0, that means both pulses were there at the same time. Delays well away from 0 means the pulses arrived separately. And it really matters who came first, right? These things look very different. I want you to note on here that 0 is kind of this placid blue color in the middle. So the really dark blue guys here are emission. And the very red guys are a lot of absorption.
And this is helium.
This is helium. So here I have filtered out all of the stuff that's above 0, just to show you where the emission features are. These are frequencies where you actually get more out than you put in, because you have done a nonlinear frequency mixing process in the gas, right? You have used the gas as a nonlinear medium to do frequency mixing. And so that has subtracted energy from most of the frequencies, but added energy to some of the frequencies in a way that really depends on the delay between the two pulses. And there's lots of other stuff going on that I'll kind of talk about. So there's 3 regions here. If the IR pulse comes first and the XUV comes second, then you see just XUV absorption, because the IR did nothing to the system by definition. And you really see that. We just get the 2P, 3P, 4P, 5P. We just get those absorption features. The width here is just our artificial window. If you don't like how wide that is, we can do a slightly longer calculation and they'll get narrower. But they are just controlled by us. So that's completely checkable. Checkable word. In here, in this overlap region near 0 delay, this is really interesting because you get lots of new absorption features. And the bright state absorption features are greatly modified, and you get these new absorption features in between the bright states. We'll talk about that. So those basically, we call those light-induced states, or light-induced structures, depending on what the referee wants you to say. Again, some people freak out when you say state, so then we call them structure. And then back here, this is the part of the spectrogram where the XUV pulse came first, pumped the system, and the IR came later. And you see this looks very different than either of the other 2 regions, right? Because what happens, this part is like the little movie I showed. The XUV comes along, it launches a wave packet by populating all the P states that are accessible. And then the IR pulse comes and moves it all around. And so you get funny absorption features. So here again is the XUV pulse comes in whenever it comes in, and it just populates every P state that it can. If I'm in the overlap region where the IR pulse is there at the same time as the XUV, then I see these extra absorption features, which you can think of as a second order process, right? First order out of the XUV pulse and either an emission or absorption process out of the IR pulse. And it ends up putting population in what is otherwise a dark state, right? If you just had the XUV pulse, you'd never get any population in the 2S state. But this process can put population there. And you actually see these light-induced features all over the spectrum because there's all sorts of second-order processes. So you can start to categorize these things by what is the bright state. So for most of the things we were looking at, the bright state that's populated is the 2P, also the 3P up here. And then the IR couples a bright state to a dark state, and it makes 2 light-induced states, one omega above the dark state and 1 omega below the dark state. That's sort of the thing. And so we can characterize these light-induced states in terms of the dark state that is being coupled to the light state in order to give you that feature. So we call this feature the 2S plus because it's 1 photon, 1 IR, above the 2s state. Here's one below. This is in the approximation that the 2s and the 2p are really close in energy. Yes?
So 2s dot and 2s minus real state. I mean, is there actual state there? Or you go and come back to 2s?
So at the end of the pulse, the population, there's some population in the 2p state and some population in the 2s state. But you see the absorption feature here and here, right? So you can think of this as like a phase coherent Raman process where you take one photon out of the XUV beam and you either emit or absorb a photon from the IR beam, right? But whenever you absorb an XUV photon, you're going to see an absorption feature at that frequency. And so that's why it shows up here.
Ken, this all started, 3 minutes ago with your showing us the emission features, not the absorption features.
Well, now I'm talking about the absorption. I'm just talking about where is there an absorption or an emission.
Okay, so this has not explained where the extra emission line was.
Yes, that's true. But to some extent, I'm not going to explain that. In other words, it's just the complicated dynamics can give you one or the other. And in any given model system, you can work it out by hand and show what form it should have. Right?
Well,
And this is, and by the way, this is very old stuff. Malo and those guys did this in the microwave regime in the early 70s.
so would it be crazy just to call them hyperamons? Could you populate 2s now? I can get hyperamons, I can get emissions
It's okay as long as they really exist only in the overlap region, which is sort of how I want to think about it here. But it's possible to actually have it extend into the non-overlap region somewhat, in which case it's kind of hard to think of it that way. So I shy away from that a little bit. But it is a sort of a phase coherent hyper-Raman process. I mean, right, a regular Raman process would not give you the striping features that you see. So, and these extra features, by the way, these have been seen experimentally by several different groups. So here, for instance, is a comparison of our theory in this. Here's the 2p line, the 3p, the 4p. Here are these extra features that show up near zero delay. Here's an experiment done in Berkeley in helium, where again you have the bright state feature, you have these light-induced state features. When you turn the intensity down, these features get much less bright. That happens in the experiment as well. They do this experiment much, much better now, but I like to show this early thing because this was sort of how the collaboration with Leone and Newmark's group got done, because I gave a talk where I showed this and Steve said, we have those. Is that what those are?
And this is all the single atom response.
This is the single atom response, that's right. But these features can't get made by propagation. So in other words, they have to start at the single atom level and kind of go forward. But the exact form of them would depend on the gas density and how long the gas is and all that sort of thing.
And the main features and we experiment.
That's right, because they're doing this at low density and stuff like that. I mean, they're trying to make it. So unlike the generation and absorption, you really can go to the low absorption limit. It's just how hard do you want to work in the experiment. There's nothing sort of in principle stopping you there.
Why in the experiment they didn't see this oscillation?
Why in the experiment what?
They didn't see the oscillation. Because in the observer they have this oscillation.
Because the laser that they're using, the XUV pulse that they're using is not, I'm sorry, the IR laser that they're using is not CEP phase stabilized, so it's jumping around all over the place. So in the experiment, they have integrated the delays over a small, like 2 femtosecond bin. So there are other experiments been done in Sang-Hu Cheng's group. Oh, I don't have that slide, I'm sorry, but where they see this beautiful striping. There's nothing. So, and you can also see 3 photon processes where this happens in the regime where the 2 pulses are separated, where the XUV comes in, it makes a wave packet, it puts population in all the various P states. And when the IR pulse comes later, It can also move population, for instance, from the 2p state, where a lot of it is. It can move by a second order process, by a 2-photon process. It can